So by the end of the day, almost all problems solved. Just one problem left, which is now how to use blockchain technology to create social bitcoins. At least theoretically speaking, Kolja Kleineberg will be the speaker.
Yes, thanks for the introduction. Really, it's a pleasure to be here today, and thanks, Dirk, for the introduction. I will talk about how complexity science can actually help to remedy certain instabilities that arise from the interaction between networks. And as Dirk said, this could be done with some incentives. I'll come to this in detail, but it also has some kind of contact points with the resilience topic that we've talked about before. So I want to start with this picture, which is called the risk interconnection map, published by the World Economic Forum. What it tells you is how a failure in one system would propagate to another. For instance, if the financial system fails, this propagates to the economy. Makes sense, right? However, these interconnectivities, they can lead to cascading failures. And how to address these failures is a very important issue. And actually, Dirk told about this a bit this morning, and also in this perspective to nature. One possible idea how to remedy this situation is to build on the intrinsic tendency of complex systems to self-organize and support this tendency with the appropriate incentives. And the first case study I want to present is how this can be done in the context of stabilizing diversity in the digital environment. In particular, I want to talk about online social networks and just give you a brief overview over this body of work. So we started looking at the evolution of isolated online social networks, and we could explain them in the sense that the network evolves on top of a pre-existing social structure, because we already had a relation with our people before we had the internet. And then you can understand the evolution just by the interplay between two mechanisms. One is a homogeneous influence of mass media, and the other is a viral spreading mechanism. And then we addressed the topic of multiple networks, of interacting networks, in the sense that we said, okay, so we distribute the attention of users between these networks, in the sense that we are more prone to give our attention to already more active networks, because we can connect to more people there. So this induces a rich get richer effect. However, we found that despite this effect, several networks can actually coexist. And here I show you the bifurcation diagram for the experts among you, and here we have a control parameter that tells us how strong this rich get richer effect is. And in a certain region of this parameter, the networks can coexist, but then it's not possible anymore. And the form of this bifurcation is called a subcritical Pittsburgh bifurcation. It means that this coexistence state is very vulnerable in the sense that once you lose it, you will not get it back. So it's like the extinction of a species, if you would. And also I want to point out that more than two networks can actually coexist. Now let's switch a little bit to topics. What are networks used for? A major application is search and navigation, which has to be done in a scalable way. And one possibility to do this is to rely on latent geometric spaces that underlie the observed topology of complex networks. And it has been shown that you can use these spaces to efficiently navigate these networks using only local knowledge. Hence, this is a scalable scheme. And what we did then, we generalized this idea to several layers of the several networking layers. And what I want to tell you here is that we found that this forwarding scheme, this navigation scheme, works better if we actively use different layers. And this is just the same as the coexistence of layers or digital diversity. So if we have this diversity, if we have this coexistence, also the performance of this navigation is better. But still we have the problem with the fragility that I told you. And to overcome this, maybe we can implement some kind of a feedback mechanism. Maybe we can reward people for doing this kind of routing, in the sense that then people have the incentive to try to increase the routing performance, which they can do by using several layers at the same time, which then can stabilize this coexistence. And to argue about this in a bit more mathematical fashion, we assume that we add an additional term which mimics this incentive to how we distribute the attention between the networks. And this additional term just gives a certain advantage to the less active network then. And here you have also a parameter that controls you how strong this effect is. So if this effect is weak, we recover the same situation as before. We again have this subcritical Pittsburgh bifurcation. And the same problem with the fragility. However, if this incentive is strong enough, we get a different situation. And just in a nutshell, what happens here is that we have, let's say, a coexistence between two networks with the same activity, and then at a critical point, this is not possible anymore. And you get, let's say, an unequal coexistence. So one network has more activity and the other has less. But the one with the less activity does not die out completely. Meaning that now when we reduce this parameter again, we will actually jump back up to the equal coexistence solution. In this sense, the system is far more resilient and robust against changes in this control parameter. Now I want to just briefly mention a completely different perspective, a topological one. And I want to again start with this picture. So here you see how these failures can propagate between different systems. But each of these systems itself is a complex system. And as such, its interactions can be mapped to a complex network. What this means is that here we have interacting interdependent networks. And these interdependencies can lead to cascading failures, which was shown, for example, in this letter to Nature, which probably most of you have read. So here we again use these latent spaces to describe a certain class of these systems called multiplex networks. And we found that these latent spaces have certain correlations in real networks. I will not go into the details here, but this example that we found before of this Italian power grid and the communication station, similar to this, which is the problem of mutual percolation or random failures. If these two layers are not correlated, you can have cascading effects that you see as a first order, or at least a discontinuous transition in the percolation diagram. However, if you have degree correlations between the layers, it's also well known that this mitigates this extreme vulnerability, and that gives you actually a smooth transition instead. And now we looked also at targeted attacks. So when you remove the most important nodes, the most connected nodes. This is very important for real systems if someone wants to attack these systems. And we found here that these degree correlations are not enough. You still have these catastrophic cascades that at these critical points, the removal of a single node completely disconnects the system. But then we found that these correlations in these metric spaces that actually exist in most real networks, they help to mitigate the situation, and they can lead to a more smooth transition, which in a real network is easier, in a real system, is easier to control, and you have more possibilities to recover in such a state. So this means that the complexity science can help you to avoid, let's say, errors to connect systems that you shouldn't connect because they don't have the similarity, these geometric relations that are actually existing in most real multiplex systems. So thank you very much. I know that this was very high level, fast, and just few very general messages. So if you're interested in the details, here are all the references. And you don't have to write them down because I will post these slides online and put a link to Twitter. So you can just follow me there and then you get all the list of references and the slides. And thanks again for your attention.